Welcome everyone. What we're going to do today is we're going to see how intermolecular forces play a role in certain properties that liquids possess. We've already seen how intermolecular forces affect two physical properties such as boiling point and melting points. We saw how the stronger the intermolecular forces present within a molecule or between molecules, how the boiling point and the melting point end up being higher. We're also going to look now at how intermolecular forces affect other properties that liquids possess, such as viscosity, surface tension, as well as capillary action. Let's start with viscosity. By definition, viscosity is the resistance of a liquid to flow. And this is related basically to the ease with which molecules can move past each other. Think of this. Some liquids that are highly viscous, they don't move very easily. There's a friction between them, so they tend to be thicker liquids such as maple syrup, molasses, things like that. Water is the opposite. Water is not very viscous, so it flows rather easily. What you're going to see is that viscosity increases with stronger intermolecular forces, and you're also going to see how it decreases with higher temperature. There's a picture of two motor oils there. They're graded 40 and 10, 40 being a more viscous liquid. Notice that the more viscous, the slower it pours out of the bottle compared to the less viscous liquid. Again, the more viscous the liquid, it's because the intermolecular forces are stronger. And what happens is, the stronger the intermolecular force, the more friction between the molecules. So the molecules don't flow or move past each other easily. There's more restriction, which makes the liquid more viscous. If you look here, these are all hydrocarbons. You could see on the table that as we go down here, the molar masses are increasing. These molecules are getting larger. They're all hydrocarbons, so they're all nonpolar. The main intermolecular force, really the only intermolecular force that these guys possess, are London dispersion forces, or LDFs. Clearly, decane has the highest or the strongest LDFs because it's a much larger molecule, therefore it has more electrons. And remember that larger molecules have more electrons, so they are more polarizable. And because of the increased polarizability, the LDFs are much stronger in decane. And as a result, you could see that as the molecules get larger and their intermolecular forces are increasing, the viscosity is also increasing as well. So again, the strength of a viscosity, or the higher the viscosity, the greater due to intermolecular forces. And you can see that here, as I wrote here, the factors affecting viscosity. So the first one, again, is the stronger the intermolecular attractive forces, the higher the liquid's viscosity will be. Another thing is the shape of the molecule can play a role. When you have molecules that are straight chains, there's more surface area, there's more contact. Again, the more contact between two molecules, the more resistance that they possess with each other, the more resistance to the flow between the molecules. If you alter the shape, perhaps if you make a branched molecule where the shape might be more spherical rather than straight chain, the molecules will have less surface-to-surface contact. The molecules will glide or roll more easily past each other. So spherical molecules tend to have less viscosity than a straight chain counterpart, due to a less surface area contact between the surface or between the spherical molecules. So that's another thing to consider, the shape of the molecules. We're also going to look at surface tension. Actually, before I do that, I wanted to mention also that earlier I had written over here that the viscosity decreases with increasing or with higher temperature. So let me take a moment to explain that. When you increase temperature, what you're doing is you're causing the molecules to separate gradually. remember that viscosity has to do with contact between molecules. So when the temperature goes up, the molecules separate a little from each other. They start to separate the more and more you increase the temperature. So if they're separating, there's less contact, which allows the molecules to move more freely past each other. So increasing the temperature will lower the viscosity because it will cause those molecules to separate, and it will reduce the friction that exists between them. All right, let's go now to the surface tension. Surface tension is another property that liquids have. According to this, it says water acts as if it has a skin on it due to an extra inward force on its surface. We're going to call these forces surface tension. What surface tension has is, this first of all occurs only at the surface of a liquid. You might be wondering, how sometimes we can see an insect literally just sitting on top of the water without it sinking. The water literally is holding these lightweight objects and keeping it afloat. Well, the reason they stay afloat is because the surface of a liquid has something called surface tension, which makes an object that's very lightweight, like one of these insects, less penetrable through the water. Now, why is that happening, and why does it only occur at the surface? If you look at the diagram that we have down here, and we can look at any single molecule, notice that if you pick any interior molecule, you'll notice that there's a balance of forces. You have some forces that are pulling down while others are pulling up. But you could see that the particle in the complete center here, there is a balance, and you could see it represented by vectors moving up and down. And you could see that that molecule's being pulled in opposite directions. Okay, so what it means is that the interior molecules, they feel no net pull in any direction. There's a balance between the upward and downward pulls. Now, when you look at a particle on the surface, you're going to notice that balance does not exist. So on any surface molecule, there is no upward force to cancel the downward force. You could see that the particles on the surface, there is a downward force, but notice that there's no upward force to cancel that downward force out. Now, what does that mean? It means that each molecule on the surface feels a net downward pull. So, how does that cause these insects to kind of stay afloat? So when a light object, there's this little object right over here, sits on top of the water, that kind of makes it act like an upward force, which would give it that feel, like if it's being balanced. So when you have like an insect sitting on the top, this molecule right over here will now experience the same effect as the interior molecules, and it will feel balanced. And by doing that, it will actually allow something very lightweight to stay afloat on top. Okay, now again, this only happens at the surface. Now, factors that affect surface tension is the following. The stronger the intermolecular attractive forces, the higher the surface tension will be. Water has great surface tension because water experiences hydrogen bonding, which is one of the stronger intermolecular forces, so water tends to have a good surface tension. Now again, raising the temperature of a liquid will also reduce surface tension. Remember that when we raise the temperature, the liquids start to move faster. They gain more kinetic energy. The important thing is that as their kinetic energy increases, they have increased molecular motion. They tend to start to separate from each other slightly, and it makes it easier, according to this, to stretch the surface. But think of it this way visually. When you increase the temperature, what's happening is these molecules have more kinetic energy. They separate from each other slightly, and it will make the liquid, the surface tension possessed by the liquid a little bit weaker, and the surface tension as a result will decrease with higher temperatures. Now we're going to look at one last phenomenon that will also explain something known as the meniscus. And the phenomenon is due to something called cohesion and adhesion. These two are kind of opposites to each other. If you look here, there are intermolecular forces that bind similar molecules to one another. When similar molecules bind to one another, we call these cohesive forces. That's why waters are attracted to other waters. So if it's the same molecule being attracted to the same molecule, we call it cohesive or cohesion. Now, intermolecular forces that bind a substance to a surface, they're called adhesive forces. Usually this is when a molecule binds or is attracted to a different molecule. Okay? What we're going to see here is the example is going to be water attracting to glass. See, water is polar and glass has a polar environment as well. Since water and glass are not the same molecules, we call these adhesive forces. Water with water would be cohesive. Now, these force of attractions are important in something called capillary action. Okay, let's take a look at that. So capillary action is the tendency of liquids to rise up a narrow tube. We call that term capillary action. And you'll notice that we have two test tubes, one with water on the left, one with mercury on the right. And I'm going to show you visually what is the difference between adhesion and cohesion. So adhesive forces attract the liquid to the wall of the tube. Remember, adhesion is one molecule interacting with a different molecule. In this case, water is being attracted to the glass, which is the tube. They're attracted to each other because they're both polar. Okay? Cohesive forces are when the molecule, the same molecule, attracts to itself. So you could see that water attracting to water would be cohesion. Now, according to this, there's a difference in why water and mercury have a different shape, which I'm going to explain in a moment. Water has stronger adhesive forces with glass. Water tends to interact with the glass way more strongly than mercury with glass. Okay, mercury has, you'll see, stronger cohesive forces with itself, meaning that mercury rather would interact with other mercuries rather than the glass. If we look at these two pictures, let's take a look at it here. You're going to notice on the left, we have water and glass interacting, which is adhesive forces. And the reason that you see it curved upwards is because the adhesion between water and glass is greater than cohesion. And you can see that right over here. Okay? The water molecules touching the glass adhere to the wall way more strongly than waters adhere to each other or interact with each other. As a result, notice that the parts of the water that are in contact with the glass rise a little higher and they form a concave surface. You can see here that the parts of the water touching the glass are actually higher, so it forms a concave surface. Now notice how mercury is the opposite. You could see here it's a convex surface, and with mercury's case, notice that cohesion between the mercuries is stronger than adhesion between the mercury and the glass. So mercury molecules touching the glass do not adhere to the wall as strongly as mercuries do to each other. So mercury prefers to interact with itself, and as a result, notice that the parts of the mercury near the glass there's not that much contact between them, and as a result, you will form a convex surface. Now, this curvature that you see due to the interactions between the liquid and the glass, okay, this little curved surface is known as a meniscus. Okay, so it's the curving of the liquid surface in a thin tube, and it's due to competition between adhesive and cohesive forces. So notice the meniscus of water is going to be concave inside that glass tube, and that's because the adhesion to the glass, between the water and the glass, is much stronger than the cohesion between water and itself. And then on the right side, you'll see that the meniscus of mercury is convex. You can see the shape is the exact opposite in a glass tube, and that's because the cohesion of mercury to other mercuries or to itself is much stronger than the adhesion of mercury to the glass. You see, mercury rather interact with other mercuries because the force of attraction between mercuries is known as a metallic bond, and they're way stronger than intermolecular attractions. A metallic bond is actually an intramolecular force, and that is way stronger than any intermolecular force. So when you have capillary action, and I'm going to draw something here real quick. Let's say you have a beaker of water here. Okay, so we got water in here, and then you put a glass, a very thin piece of glass with an opening. You're going to see that the water there'll be a tendency of the water to rise higher inside the glass, and of course it'll be a concave surface, but you'll see that you would expect maybe the water would be here at this level, but you'll see that if you look inside the tube, it's actually going to be higher in the tube, and that's because, again, the adhesion between water and the glass is stronger, so it tends to rise higher inside that tube. Okay, so I want you to keep that in mind. This tendency of a liquid to rise up these narrow tubes is what we call capillary action. And all of this intermolecular forces plays a role. And these properties that you just saw are unique properties that liquids possess.